Welcome back to Element 14 Presents. I'm Clem, and do you know what the difference between a Raspberry Pi and any other normal computer is? It's basically just the GPIOs, the general purpose input-output pins. But what if we could add these pins to any computer? There would be plenty of project ideas for all of these old laptops if we can just add GPIOs to them. Let's try that. The GPIO pins act as a connection to the outside or the real world, basically, so we can use code to interact with other things, like different devices that we put on a bus, just putting pins high and lows to light up LEDs, or to activate and deactivate relays or other stuff. But it's basically about putting code into the real world. So we need one common denominator for all these old laptops, all the basic computers that you have around, or maybe you just want to have more than just these pins on a Raspberry Pi and add like a second full row of them to your projects. Well, the common denominator for all of these is one thing that you all know. When I started my computing journey, USB was a very new thing. My first computer that had it was in 1998, and we weren't really sure if that would catch on. Yeah, it was just the new thing. But turns out now USB is the common standard that pretty much any computer uses. Either it has just a USB port or there is a way to add it internally. So we're using USB to GPIO bridge. Or no, we're building a USB to GPIO bridge. From scratch, of course. You know what? I can directly show it to you. This is the GimmeGPIO, and by not a coincidence, it has the exact same size, form factor and pinout like a Raspberry Pi Zero. You can even connect them directly together for no particular reason. But this is not just looking like a Raspberry Pi Zero, it also follows the same pinout and the pins have the same capabilities. And now I'll show you how I made this thing and why and basically all the in and out. And if you look closely, you can see that this PCB board is really thin, like really thin. So how does it work in practice? Well, you take your computer, you type in commands, and the GPIOs will act accordingly. Pretty similar to what you can do on a Raspberry Pi by interfacing with the GPIOs directly. But of course you can also use them via code. So I've made a Python library that you can just include in your projects, and all of a sudden you have full control over the GPIOs. You can set pins high and low, put PWM values on them, and even relay communication protocols back and forth. The last part, there's a bit work left to do, but the basic functions already work. And the more interesting bit is, how do you make that with just a microcontroller, a GPIO header and a USB port? Of course, I can't just solder random parts together and hope that it works. I need a plan. So to create this thing, I had to design a PCB in KiCad, of course, and thanks to Eisler, I got it made in 0.8 millimeter thickness. This is a 4-layer board and it's extremely thin. This is perfect for embedding it. So if I want to make basically a version that I could then just embed into, maybe into an old laptop. Interesting project idea. Anyway, the super thin boards are perfect for embedding it into stuff, or if you make modules that go onto stuff, which this could also be in the future. The most important project is to select your parts carefully. I did it via using parts that I already had on hand, but I selected them carefully. This is an ESP32S2 for two reasons. It has native USB support and there's still hardware UART left, so I can relay data from the USB port to the hardware UARTs without losing much speed. Our bottleneck will still be the USB 2.0 speeds that we have via this port, which shouldn't matter that much for most of our projects. And the other thing is, this has enough GPIO to populate the whole header, but also these GPIOs are pin maxed, means that I can adjust all the functionalities that these pins have available to my layout. So I'm not restricted by the pins actual definitions, I can change them even dynamically. So while this now adheres to the Raspberry Pi pinout, it doesn't have to. I could still change that and move, for example, an I2C port to some different pins and they would still work fine. If you decide to recreate this project by downloading all the files for free on the Element 14 community page for this project, then you may want to have a case. So I quickly designed a plate-based case for you just to download, 3D print, laser cut, whatever you want to do with it. I also did a first now because I printed this in PETG and used my fiber laser to engrave some writing on it. Never tried it before, and it gives beautiful white marks on black plastic. So that's another first for this project. You also may recognize that we're in a new place. That's another first. Did that project not have any trouble? Well, it did. If you screw on the plate cover too tight onto the PCB, then you bend the PCB and it can stop working. This happened to me. Don't over tighten your cases, especially if you're using very thin boards. These are a bit delicate. Still happy to have tried it out. And you know what? We should talk a little bit about the code. Welcome to the dark void of code. So the whole device works on a USB to UART kind of to GPIO interface. So we're having a serial protocol that you can directly interact with over a serial terminal, or you can send the commands via code. As I said, I made a Python library to make that super easy. Because most people use Python on a Raspberry Pi, I thought that was a fitting way to interact with it. The other thing is that we have functions for each of the tasks that a pin could fulfill. So each of these is contained in a function, and we call each of these when the write command is issued. They follow all the same structure, the type of command, what pin, and what we do with that pin. And some of them, like the I2C write, have I2C write because the I2C pins are kind of fixed on a Raspberry Pi. Then we have the address and then whatever we write to it. We can also read, of course, from the pins, be it digitally, serial protocol, or analog. Analog reading on the Raspberry Pi wasn't the greatest thing in the past. It's also not the greatest thing on an ESP32, so we're quite on par with that one. But what really is nice is PWM writing. And that's because the ESP32 has a utility called LEDC write, which is basically meant for LED brightness adjustments. So there is a PWM channel running constantly all the time, and you have multiple channels to configure. I've used this in a previous project very extensively. One major thing changed, and I want you to know that there was an update to how the LEDC write stuff works. I've put in the old way and the new way in the code that you can download so you can see the differences. Be aware that if you ask LLMs or some older tutorials online, you may get the wrong answers and they won't work anymore and not compile. That's why it's important that you don't trust random sources on the internet, but you actually try them out if they actually work. Okay, that's pretty much it. You can check out all the files, all the code on the Element 14 community page. And I have to leave this void because it's kind of closing in on me. Oh, back in the normal world, one thing left to do is actually try it out. So I connect this not to any computer, but to my main workstation, which is an amalgamation of random server parts that are about 10 years old. But it still works, and we can add GPIO even to that abomination. You can see me now use the serial interface just via the Arduino IDE, but any other serial terminal would of course work. I can just issue the commands and I probe these pins that I set with an oscilloscope. And with the oscilloscope, of course, I can see the logic level that is currently on there. I can also read back from the pins. I can issue serial commands. They are a bit hard to capture because they are very fast happening. But I can also change PWM values, and those you can see really clearly on the oscilloscope. So this works like a treat. It's actually the hardest part about it is probing the pins because the GPIO pins on a Raspberry Pi header are pretty close together. I happen to have a lot of these, so this could be a thing that I could make a lot more of, because I also have like a lot of old computers that might need some GPIO in their lives. Thanks to our GimmeGPIO project, I don't have to use Raspberry Pis for everything now. I can reuse old laptops and just use this little board, add it to the machine, and then I basically have a device for a lot of other projects where they just don't have to be so small. Speaking of other projects, I gotta go. There's another project waiting for me. Oops, I dropped it.